Okay, so we're on linear functions. Linear functions are a super special type of function, and I'll share why in a bit. But we're going to unpack what makes a function linear and how can we tell if a function is linear with this little video lecture. But quickly, I want to say why linear functions are so special. And they're special because they're simple. You've definitely seen linear functions before just by looking at graphs. It's the simplest graph you can draw is a linear function. And again, the reason it's so powerful is because it's so simple. It's a way to draw a very basic relationship between two quantities. So if x is the number of hours you worked and y is your paycheck, a linear function is a perfect fit and tells us exactly what we need to. And in things that are highly complex, like the forces between two particles, if we zoom in far enough and we kind of strip out some of the confounding variables, we can still draw a linear relationship at certain times. And so it's powerful. Even at the highest levels of analysis, linear functions still come into play. So it's the first function we look at, and it's also something that is used all throughout mathematics because it's really just a simple kind of drawing of a relationship between two things. So linear functions, just super important, probably the most important function of all time. I'll assert my biased opinion here. Most important function of all time. If anyone of us is going to calculus, essentially calculus is trying to make the world linear when it's really not, and they got by that major issue by being very creative. And that's kind of the genius behind calculus. But anyway, we're going to answer these two questions. Question one, what makes a function linear? Well, one of the key things that makes a function linear is the fact that its rate of change, how much it changes in y over how much it changes in x, is the same ratio no matter where you are. Function is linear. It has a constant rate of change. So this is the biggest idea here. Function's linear if it has a constant rate of change. And a constant rate of change, CROC, equals the average rate of change for a linear function. Right, so if you measure the average rate of change between any two points in the function, it should always be the same. So let's look at a simple example. So if P of t equals 200 plus 20t, is a population in a small town after t years from 2010. What is this? And let's say let's go from 15 years to 5 years. So we can go in and calculate this. So P of 10 is 200 plus 20 times 10, which is going to be 400. P of 5 is 200 plus 20 times 5, which is 300. And P of 15 is 200 plus 20 times 15, which is what, 500. And so we can substitute these in here. So P of 10, 400 minus p of 5, which we said was 300, over 10 minus 5 is 5. We see that's 100 over 5, which is 20 over 1. It's the average rate of change. Again, this is 20 people per year. And then if this is linear, that means this average rate of change, they should all be the same. So p of 15 minus p of 5. Well, p of 15 is 500. P of 5 we said was 300. All over 15 minus 5 is 10. Well, that's 200 over 10, which is also 20 over 1, 20 people per year. So it seems that this is a constant 20 people per year, and it turns out if you do this in any 2 points, it will always be 20. And that's really coming from the structure of this thing. If you look at how this function changes, we're starting with 200, and then for each t, as t increases from 1, 2, 3, 4, etc., it's getting multiplied by this 20. So for each 1 that goes up, we're getting multiplied by 20. That sounds like 20 per 1, right? A change of 20 per a change in 1. So a function is linear if it has the same rate of change everywhere. We call this constant rate of change the slope of the line. And we give it a name m. We say for any 2 points on the line, if y equals f of x, slope m is given by any f of b minus f of a over b minus a for any 2 points in the function. And this should look eerily familiar as the average rate of change formula, and it is, right? And I like to write this in a better way, which is this is equal to the change in the output over the change in the input. And we measure change again by the difference. So the difference in the function's value over the change in the input. And again, we say that this is the constant rate of change for a line. So let's look at an example here. We'd say, what is the slope of the line or of the linear function where f of 6 equals 11 and f of 8 equals 18. Okay, so I know for a given input-output pair and a given input-output pair that the slope or average rate of change between them, is going to be the slope of this line, because for a line the average rate of change is the constant rate of change. So I'd be looking at change in the output over the change in the input. Again, this delta means the change, so that means the difference. So the difference in the output, well, the output is 11 and 18, right? So that's 18 minus 11 over the change in the input. Well, what's the inputs are here? So that's 8 minus 6. And again, it's important to use the order end minus start when measuring slope, because subtraction is not commutative, so that order does matter. So 18 minus 11 is 7 over 2. So what we say is that the slope m is 7 over 2. What that really means is for every increase of 2 in x, we increase by 7 in the y direction. And remember that this slope, this change in the input over the change in the output, is really, you hear this referred to a lot as the rise over the run. right? Rise is how high the function goes based on how far over you're moving with your independent variable. So change in the output over change in the input is the rise over the run. So obviously you can see how important it is to remember, which is the input, which is the output for given functions like this. So we can find the slope numerically in this way. And we're going to answer the question as well, how can we tell if a function is linear? You might be able to answer this already. Basically, the one way we've talked about already is that the average rate of change is equal to the constant rate of change. That's one way. Another way is if it's of the form y equals b plus mx, which we will unpack more later, or can be written of the form y equals b plus mx, where again m is your slope. Other way you could look at it is if the graph is flat, but you got to be careful. Why am I saying be careful? Well, I'll give you one example of how you could be fooled by a graph. Let's say I give you the graph of a non-linear function, so something like this, the parabola. And for some reason, let's say we zoom in on your calculator to maybe just this piece right here. We scoot this over, and this is your window now. And it just looks like this to you. It's not unreasonable. If you zoom in really far on something, right, even the biggest curves will kind of tend to straighten out. So, if you look out at the horizon, it looks flat. Really, the Earth is curved, right? So if you zoom in far enough, things will start to look straight. So we know that the graph should be flat, but we need to be very, very careful about that. We need to probably verify with another method that the constant rate of change is the average rate of change. Okay, so you can look between multiple points to kind of double check that that's the case, or you can look and see algebraically if it's equivalent to b plus mx. But again, we're going to work more on that later. So if you have any questions on this, be sure to hit the class discussion forum, and just be really mindful of the notation being used here for the average rate of change formula, and I was also going to say this formula here for the slope. Change in the output over change in the input is what gives you the slope for a line, or the constant rate of change for a line. So again, you can predict what the units are going to be of this. If you're talking about a paycheck, this is going to be dollars per hour. If your input is time and your output is the paycheck, you can talk about miles per gallon if you're talking about distance gone per gas used. Right, these are going to be rates of change. Alrighty, that's enough for me. Enjoy.